Okay, welcome back. Here we've got a forensic chemist, and chemistry is really important in forensic analysis, particularly when we combine the techniques that we've been learning about. This lesson we're going to look at combining techniques. So in this lesson we're going to look at deducing structures of organic compounds and also how we can look at the purity and identification of organic compounds using the techniques that we've been learning over the last few lessons. So you're expected to understand how to use each of the techniques individually and in combination. So the data obtained from mass spectrometry, proton NMR, carbon-13 NMR, and infrared spectroscopy can all be used to determine the structure of an organic compound. For mass spectrometry, we can determine molar mass by looking at the mass charge ratio of the parent molecular ion. And we can look at possible branching patterns, which is looking at the fragments. From infrared spectroscopy, this is useful for functional group, the presence or the absence of functional groups at a particular wave number. And that requires looking at the data book for the wave number. 13 carbon NMR tells us the number of non-equivalent carbon environments, excluding TMS, which tells us the number of unique carbon environments present in a molecule. Proton NMR, if it's high resolution, tells us the number of non-equivalent proton environments in the molecule by the number of peaks, excluding TMS, the ratio of protons in each environment, which is the area under the curve, the types of proton environments present, looking at chemical shift, and comparing that to the data book, and the number of protons in neighbouring proton environments using the N+1 rule. Okay, let's look at an example. So we're told that C3H6O can exist as a ketone or a primary alcohol. Let's sketch the molecules so we know what we're talking about. So if we've got a 3-carbon ketone, we've got a carbonyl group that's not on a terminal carbon, well, that would be an aldehyde. So here we have propanone and primary alcohol. So if we have a 3-carbon chain with a hydroxyl group on a terminal carbon, here we could have propan-1-ol. So there's many different ways of answering this question. And if you're interested, you can go to the examiner's report for this question 2020 and see all the acceptable answers that VCAR accepted. But we're looking for a principle by which IR operates, a principle by which proton NMR operates, and then an example of how we can use the proton NMR to differentiate between the two molecules and the infrared spectrum to differentiate between the two molecules. So IR measures the change in vibration of atoms in a bond in the molecule and can give information about the type of functional groups present or absent in a molecule. So that's the first mark. Proton NMR involves the absorption of radio waves resulting in various chemical shifts that correspond to the neighbouring proton environments. So that's the second key point. Primary alcohols show a shift of 3.3 to 4.5 part per million for hydrogen atoms adjacent to the hydroxyl functional group, and a singlet between 1 and 6 part per million. So that's using data from the data book to explain how NMR would be used. In IR, a primary alcohol will contain an OH alcohol bond with a distinct peak that's quite broad between 3,200 and 3,600 centimetre minus 1, and that's referring to data from the data book. So as long as you've got 4 pieces of information, there are many ways of answering this question. Okay, now we're going to look at how we can use combining techniques to work out purity and identification of organic compounds. So LCMS stands for liquid chromatography and mass spectrometry combined technique. And it's a combined technique of both HPLC and mass spectrometry. And the purity of a compound can be determined using this technique. Applications include forensic science, petrochemical analysis, pharmaceutical science, and environmental analysis. Okay, we can use chromatography or HPLC specifically to detect the presence of impurities. An impurity is a constituent which interferes with a purity of a substance when there's nothing else present apart from its solvent. So if a sample is pure, we would expect to have just one peak using HPLC. So this chromatogram shows the presence of 1, 2, 3, 4 components. So this substance would not be pure. We would expect to have a single peak for a pure substance. We can also use spectra for environmental analysis. Here we have infrared spectroscopy, and we can identify an impurity if we get a difference in the two spectra. And we can notice that we've got a strong absorbance peak at 2,700 centimetre minus 1, which is on both spectra. And we have the same if we could overlay the fingerprint region from up to 1,500 centimetre minus 1. We can see that that pattern is the same, so we could say that there's no impurity here. So a sample of city air matches the known standard of this particular volatile organic compound. Okay, let's summarise what we've already learnt. So we can get lots of different information from the various techniques. From mass spectrometry, we can work out molar mass and possible branching patterns looking at the fragments. Infrared, we can look at the presence or absence of particular functional groups above the fingerprint region, so 1,500 centimetre minus 1 to 4,000 centimetre minus 1. 13 carbon NMR, we're looking at the number of non-equivalent carbon environments, and that tells us the number of unique carbon environments present in a molecule. And proton NMR, the number of non-equivalent proton environments, which looks at the ratio of protons in each environment, the types of proton environments present, and the number of protons in neighbouring proton environments. Applications of all these techniques include forensic science, petrochemical analysis, pharmaceutical science, and environmental analysis. Coming up next is Chapter 10 review. See you then. Bye.